We've now completed the proof of the following theorem. Let f be a field and fix the polynomial g of x in f bracket x. The first part of the theorem says if g of x is factorable, then the quotient ring f bracket x mod the ideal bracket g of x is not a field. And for example, we've examined z7 bracket x mod bracket x squared minus 1, which factors as x plus 1 times x minus 1. The second part of the theorem says if g of x is unfactorable, then the corresponding quotient ring is a field. And the example we've seen, r bracket x mod bracket x squared plus 1, where x squared plus 1 is unfactorable in r bracket x. A key ingredient to the proof of the above theorem was the GCD theorem for polynomials, which is a tool from number theory. But since this is an algebra course, we like to prove this theorem again, but this time using a tool from Abstract Algebra. And that's what we're going to do for the last 2 lessons of this course. Now, the Abstract Algebra tool in question are the ideals. So let's start with a review of that concept. Here are the opening questions. Part A, what does it mean that 12z is an ideal of the ring of integers z? Part B, find all ideals A such that 12z is a subset of A, which in turn is a subset of z. In other words, the ideal A is sandwiched between 12z and z. However, with the restriction that the ideal A cannot equal one of the endpoints, namely 12z or z. Then part C, same as part B, but with 12z replaced by 5z. So if you could pause the video and try these questions, and we will go over them shortly. Let's start with part A. We say that 12z is an ideal of z if 2 conditions are satisfied, namely 12z is an additive subgroup of z and also satisfies the product absorption property. This is the property where if you take an element from 12z and an element anywhere in z, multiply them together, that product is still in 12z. Part B, find all ideals that are sandwiched between 12z and z, but doesn't equal either of the endpoints. And here are the possibilities. The ideal A could be 6z or 4z or 3z or 2z. And because A doesn't equal one of the endpoints, 12z or z, we say that the ideal A is strictly between 12z and z. And what about part C? Is there an ideal that's strictly between 5z and z? And the answer is no, there is no such ideal. In fact, if we were to sandwich an ideal A between 5z and z, the only way to do it is if A is one of the endpoints, namely we must have A equals 5z or A equals z. Now, the ideal 5z in the previous slide is an example of what's called a maximal ideal of z. In other words, there's no ideal that's bigger than 5z, and that's why we couldn't sandwich a different ideal between 5z and z. And here's a definition. Let M be an ideal of a commutative ring R. So in the above example, 5z plays the role of M, and z plays the role of R, with M not equal to R. Then we say that M is maximal in R if for any ideal A that's sandwiched between M and R, we must have A equaling one of the endpoints, namely A equals M or A equals R. And so what this is saying is that there is no ideal A that is strictly between M and R, that doesn't equal either one of the endpoints. We've already seen an example of a maximal ideal of z, namely 5z. So let's take a look at a non-example. Based on our work in the previous slide, we can say that 12z is not maximal in z because there is an ideal, such as 4z, that fits strictly in between 12z and z. Consider this notation, which looks like the subset symbol with a little slash across the horizontal. And it means that 12z is a subset of 4z, but does not equal 4z. Likewise, 4z is a subset of z, but does not equal z. In other words, 4z, the ideal 4z, is strictly between 12z and z. And here's a visual depiction of this situation. We have the ideal 12z inside z, and the reason why 12z is not maximal in z is because we can sandwich another ideal, such as 4z, right in between, strictly in between those two. And so let's label this 4z. And to show that 4z doesn't equal either of the endpoints 12z or z, we can produce, say, an element that is inside 4z but does not belong in 12z. So that would be a multiple of 4 that is not a multiple of 12. 8 would be an example. Likewise, to show that 4z doesn't equal z, we would have to produce an element of z that is not in 4z. So an integer that's not a multiple of 4, for instance, 1. And so this shows once again that 4z is strictly in between 12z and z. Now please pause the video and work on day 36 classwork. Afterwards, we will go over some of the problems and concepts. Let g of x be the polynomial x squared minus 1 in r bracket x. In the classwork, we showed that the ideal bracket g of x is not maximal in r bracket x, since there is an ideal that fits strictly in between bracket g of x and r bracket x. And that ideal is bracket x plus 1. Now note here that the polynomial x squared minus 1 is factorable in r bracket x. It factors as x plus 1 times x minus 1, and therefore x plus 1 is one of its factors. And we used that factor to construct an ideal that fits strictly in between bracket g of x and r bracket x. And that's what makes bracket g of x not a maximal ideal. This example suggests the following proof know-how. To show that the ideal M is not maximal in R, find an ideal A that fits strictly in between M and R, as follows. For the next example, let g of x be the polynomial x squared plus 1, which is unfactorable in r bracket x. We then claim that the ideal bracket g of x is maximal in r bracket x. And here's a proof know-how, which we will use in our proof of the day later in this lesson. To show that the ideal bracket g of x is maximal in r bracket x, consider an ideal bracket p of x that fits in between bracket g of x and r bracket x. In other words, bracket g of x is a subset of bracket p of x, which in turn is a subset of r bracket x. Then, show that this sandwiched ideal bracket p of x must be equal to one of the endpoints, namely bracket g of x or r bracket x. And this shows that we cannot fit an ideal strictly in between bracket g of x and r bracket x, and therefore we can conclude that bracket g of x is maximal in R bracket x. And here's the theorem of the day. Let f be a field and fix a polynomial g of x in f bracket x. Part 1 of the theorem says if g of x is factorable, then the ideal bracket g of x is not maximal in f bracket x. Our earlier example, using the polynomial x squared minus 1 in R bracket x, suggests that we can construct an intermediate ideal using one of the factors of g of x. Now, part 2 of the theorem says if g of x is unfactorable, then bracket g of x is maximal in f bracket x. And we will give a proof outline of part 2 in the next slide. And please also see chapter 36 in the textbook for the proof of this theorem. So here's the theorem. Let f be a field and fix a polynomial g of x in f bracket x. If g of x is unfactorable, then the ideal bracket g of x is maximal in f bracket x. Our goal then is to show that bracket g of x is maximal in f bracket x. And we will take the approach described in one of the proof know-hows from earlier in the lesson. So, consider an ideal bracket p of x that's sandwiched between bracket g of x and f bracket x. We will then show that bracket p of x must equal one of the endpoints, namely bracket g of x or f bracket x. And again, this tells us that there is no ideal that's strictly between bracket g of x and f bracket x, which will imply that bracket g of x must be a maximal ideal. And next, we will use the inclusion bracket g of x is a subset of bracket p of x. Well, we know that the polynomial g of x is contained in the ideal bracket g of x. And as highlighted above, bracket g of x is a subset of bracket p of x. In other words, the polynomial g of x must be contained in bracket p of x, which means it is a multiple of p of x. So we can write g of x equals p of x times another polynomial q of x. But our hypothesis says that g of x is unfactorable. And so this factorization can't possibly be a legitimate factorization. And therefore, one of its factors must be a non-zero constant. And please refer to chapter 36 for the technical details. But it turns out that if p of x is a constant polynomial, then bracket p of x equals f bracket x. And if the other polynomial q of x happens to be constant, then bracket p of x equals bracket g of x. In either case, we've shown that bracket p of x must be equal to one of the endpoints, namely bracket g of x or f bracket x. And therefore, we can conclude that bracket g of x is maximal in f bracket x as desired. And so that's the proof outline, and that's also the end of this lesson. So I will see you next time.